Hello.
Hello. So my wife has a question because I was just showing her how we do this because she's got to do a presentation in about a week or so. And so the question that she had is when I'm sitting here at my computer, I have the presentation off to the side, which you guys should be seeing lecture 7, September 10th to get started on the PowerPoint. But
Yes.
while I am talking and doing my thing, do you guys see like a little window somewhere that has me like live in the window? Does that show to you?
Yes.
Yes. Yeah.
Oh. So even while I'm doing this live, you can see me right now wearing a baseball cap.
Yes.
Yes.
Usually,
Yes.
it,
On the hoodie.
usually it'll show like the person who's talking in the little window.
Oh, okay. All right. So you see me with my baseball cap and my hoodie on right now. Oh boy. All right.
Yeah.
Um, I got to debate whether or not I want to tell her that or not. I don't want her to freak out. Okay. All right. Thank you. Thank you for sharing. As we start tonight, this is lecture 7. And before we get started, does anybody have any questions they would like to ask about homework or what they've read in the text or what we covered in the past?
Professor.
Yes.
I was doing the homework earlier today, and there was a question about modulus of resilience and the modulus of toughness. I
Yes.
just didn't know what toughness was, like if there was like a specific formula for it, or
Yes. Yes, there is. Did you catch last lecture?
yeah, but I must have missed that when we were doing lecture.
Okay, no problem. No problem. So the modulus of resilience is the area under the stress strain curve up to the proportional limit. And the modulus of toughness is very similar, but it is the area under the stress strain curve from the origin all the way to the point of fracture. It's the area under the whole curve. That's the difference between modulus of resilience and modulus of toughness. And bear with me a second. Strain energy. Okay, so in your text, modulus of resilience is defined on page 95. Modulus of toughness is defined on page 96. And then also, if you like, you can find my YouTube video. I posted a link to it. If the link doesn't work, by the way, because I fat fingers, I put in the wrong letter or something, you can always just do a search under Aaron Pratt or Mechanics of Materials Aaron Pratt, and I'm sure they'll get you to the same place where you can see all those videos. Watch the last video because not only did we cover modulus of resilience and modulus of toughness, but I talked about why the modulus of toughness, why would anybody care? And we talked about seismic and Northridge and Charpy notch tests and all that stuff. So that was kind of all wrapped up in that whole presentation.
Thank you.
Yes, yes, of course, no problem. Also, let me also, I don't know if somebody had this question or not, but this question comes up a lot. So let me just talk about it for a minute, and then maybe you haven't got there yet, but maybe this will help. If you look in your textbook, there are problems on page 102, 103, and the author gives you a stress strain curve for a material. But what he has done is he's broken the entire curve into 2 curves, and he superimposes them on the same graph. And so you have this stress strain curve that looks sort of like what I did, only the straight line portion of it is on the lower half of the graph, and the plastic strain hardening portion of it is on the top half. And so when I first saw it, it was very confusing. I was like, well, wait a minute, which one is it? What material are we talking about? But what he has done is the The elastic portion of the total stress strain curve is such a small range on the strain that it's almost imperceptible to see it. So he's basically taken the first 0.035 portion of the strain curve and magnified it. And then the rest of the curve is not magnified. So if you look at the bottom of these curves, you have strain that's in blue numbers. That's for the magnified portion. And then you have strain in black numbers. That's for the not magnified portion of it. And if you look really close, there's a little bit of a gap on the upper curve, the strain hardening curve. There's a little bit of a gap there between the zero axis and where the curve starts. Well, the bottom curve with the two straight lines fills that little gap. So the whole bottom portion squeezes into that little gap on the top portion. Okay, Mustafa, what is the formula for getting the area under the entire curve, the modulus of toughness? There is no formula because there's no mathematical expression that describes the strain hardening portion of the curve. So I've done it one of two ways. The way that I've done it is I took each one of the data points and I interpolated what the KSI was at that point. So like say your grid points are 0.4, 0.8, 0.12, 0.16. I interpolated or eyeballed the KSI at each one of those points. And then I formed a trapezoid between that point and the next point and got the area of a trapezoid. And then I did that for each one of those columns until I've basically approximated the area under the whole curve by interpolating along each grid. That's one way to do it. That's the way you'll see it in my solutions. The other way to do it is to calculate the area of one square on the grid and then count the squares. But that's not nearly as accurate though, because when you get to the squares where the line goes between the squares, you kind of have to just eyeball, okay, is that a quarter square? Is that a third of a square? How many squares is that? But that'll get you in the ballpark as well. But there's no equation to do it because there is no mathematical expression for that portion of the curve that's in strain hardening. As opposed to the modulus of resilience, we had an equation to get you there because it's a straight line. So the equation for the area of a triangle is something that we can express. Did that help with the question?
Yeah, thank you. And I think it's different because it's like differ the material, and like different in each material. Like
it is
different curve. That's why maybe.
Yes, yes. The shape of that strain hardening is different for every material. And like I said, sometimes, well, it's just different for every material and there's no expression. It's really a experimentally found shape, not a mathematically expressed shape. Any other questions before we get started? Okay. Well, then let's talk about tonight. You know what? Actually, before I do that, let me pull up something real quick. Come on, there you are. Okay. So let's see, today is the 10th, 17th, 24th. So 2 weeks from tonight will be our first midterm. And we'll talk about that a bit more as we get into next week. But please be prepared to be online and ready to take that test at the 5:30 to 6:45 slot on that midterm. We're all going to take the midterm at the same time. Basically, as I understand it, the campus, Cal Poly, has broken their contract or not renewed their contract or whatever it is with Respondus. So we don't have Respondus anymore, the plan is going to be, this is what we're going to do, a Zoom meeting, just like we always do a Zoom meeting for the lecture, only we're going to do a Zoom meeting. I'm not going to share my screen. I'm just going to sit here for an hour and 15 minutes and stare at all of you while you are taking the test. That's the plan. So that means we all take the test at the same time, and we all scan it and send it up to me at the same time. So I have not written the test yet. I don't know what's on the test yet. I'm going to try to get to that this weekend or in the coming week. But for now, I just want to give everybody a heads up that on the 24th at 5:30 p.m., you really, really want to make sure you have good Wi-Fi and that you are able and willing to be on that Zoom call at that time, because that is the one time we're going to do this test. Okay?
Professor?
Yes?
I'm your student from Indonesia, the one who couldn't find green engineering paper. So for the midterm, do you want me to do it on maybe like a white A4 piece of paper, or stick to my doing it from my tablet?
Well, without Respondus, let me put it this way. I have no problem with you using the tablet, but it's still, you have to still be able to have your webcam on so that I'm watching everybody at the same time. So basically, everybody has to be able to have a live webcam during the test.
Oh, okay. All right. Got it. Thank you.
Okay.
So you said we can use our tablets now that we don't have to use that lockdown browser?
We're not using the lockdown browser, right?
Professor, you said it was going to be open book and open notes, right? And then one page of cheat sheet?
That's right.
Okay.
That's right.
I have a question, Professor.
Yes.
Are we also going to have our tests scanned and submitted by the hour and 15-minute period?
No. No.
Okay.
No. I'm gonna set it up so that the test portion of it is going to shut down at 6:45, and so the test will be available at 5:30. The test will not be available after 6:45. So that basically means pencils down at 6:45. But then once the pencils are down, I'm going to give everybody a reasonable amount of time, 15, 20 minutes, to scan up their work and send it into Blackboard.
Professor, so the midterm on should be on Thursday. Are you gonna including the material which we will cover on Tuesday?
No, we will not. But I do not know yet exactly where the cutoff is. But most certainly the Tuesday before the Thursday is not going to be covered on Thursday. That would be very unreasonable. But the Tuesday and Thursday of the week before very well may be. I'll give you more information as we come along. Okay? If anybody was just tuning in late, please get from your classmate everything I just said, or you can watch the YouTube. I guess it's all being recorded. So you can watch the YouTube and get the information that you need for the midterm. I will give more information, as I said, as we get into next week or so. But the information you need to know right now is that you must be available for the test at 5:30 on the Thursday, September 24th. If you are late to that Zoom meeting, you just have less time to complete the test. That's how it's going to work. Okay? I said I just wanted to kind of broach the subject so that we're not like a few days away and say, oh, by the way, everybody has to do it this way. Alrighty. Let's go. Okay, so tonight we're going to start with this Saint Venance principle. That's where we're going to start tonight. So this is how I'm going to describe this principle. if I have a bar or plate of material and I apply a point load to this plate material right here at the center, and I have a point load applied to a bar, creates a disturbance at the point of application. In other words, right at the point that I'm applying this load to it, the stresses are not going to be even and nicely distributed. They're going to be irregular. So if I look at the stress distribution at a cut AA, we can see, and AA is just below the point here, we can see that the stress is not evenly distributed as predicted by sigma equals P over A. And so this might be what the stress distribution might look like at this cut A. So directly under the point load, the stress is pretty spiked, and out towards the edges, the stress is fairly low. Due to the discontinuity of the point load, the stresses will spike under the load. The average stress at AA does equal sigma equals P over A. So if you're to take an integral of this, sum up all the stresses and take an average, the average is still P over A. But the peak stress can be many times higher than the average. Okay, does this read for everybody? Does this make sense? If we look at a stress distribution at a cut BB further away from the point load, we will see that the stresses have somewhat smoothed out. So now I'm twice as far from the point load at BB. So this was at AA, here's at BB. So it's not quite as lumpy, it's smoothed out somewhat. If we continue away from the point load at a cut CC down here, we see that the stresses have averaged out to equal sigma equals P over A, like so. So now at some distance away from the discontinuity, and a discontinuity can either be from the loading, or the discontinuity could be some change in material shape or in a change in the material itself. Any kind of discontinuity that would disrupt the stress flow is a discontinuity. So at some distance away from the discontinuity, then the material will be experiencing a stress that is equal to P over A, which is the average stress as shown. So the stress here is P over A. This also applies to physical discontinuities. So here I've taken the same bar, but now I punched a hole through it. So at section AA, where the hole is, I have these stress risers. This discontinuity causes this increase in stress. And this really happens, by the way. They're called stress risers. And whenever you have a discontinuity, you create a non-uniform stress like so. At the hole, the stress is highly disrupted. If we move down a bit to cut BB, so now BB is right at the bottom of that hole, you still have this very discontinuity of stresses. And right at the bottom of the hole, there actually is no material there, so the stress has to equal 0 at that point. But the same principle applies. If I go some distance away from this discontinuity, say at a cut CC down here, I am back to the stress is equal to P over A. So St. Venant's principle is at some distance away from a disturbance, stress and strain are equal for equivalent loading. The distances is approximately equal to the widest dimension of the section. So in this bar or plate, if the widest is designated as L, then the distance where the stresses basically smooth out to be the average P over A, then that is about approximately a distance L from the discontinuity, as shown. You know what? I did not answer. I did not answer all these questions. Let me just take a second here. Mustafa, you had added 4 or 5 chapters. I don't know yet. We'll get into where the cutoff is for the midterm. Adriel asked, how many questions do you usually do? For an hour and 15-minute test, I usually do 3 questions. For Cassidy, do we still have to have the printed version of the book? Well, I guess the answer is no, but you're going to, I think you're going to want a printed version of the book or a printed version of the portions of the test that you're going to be tested on, because the test is going to be on your screen. You're going to be solving it on a piece of paper, and it's up to you, but it would be cumbersome, I think, to keep having to switch back and forth between what's on your screen. Daniel, so the midterm is on the 24th. The midterm is on the 24th at 5:30. And I guess that was it. Okay.
Professor, just another quick question. So I know we have to have our webcam on. Do we have to have our mics unmuted as well?
No, I don't want to hear you cussing.
Okay.
No, I don't want to hear all that. You know, I think you guys might like me until I listen to you. Then you know, I would know the truth. I don't need that. No, I'm just kidding. You don't have to have your mics on. The idea, of course, is just test security. And the idea is, yeah, cussing or crying. The idea is that you ought not to be texting a classmate and say, hey, what'd you get for number 2? I'm stuck on 2, part B. What'd you get? Or talking on the phone or looking up answers or things like that. I mean, we're in this situation. It's the best we can do. But I'm trying to make the test as fair as I can for everybody. So the obvious texting on the phone, calling people on the phone, at least if you know that there's a camera on you, watching you the whole time, hopefully it creates a fair atmosphere where everybody has the same opportunity.
One more question.
Sure.
Do you want us to print out the questions, or is it fine if we just write the solutions down on a piece of paper and scan that?
The latter is just fine.
Okay.
I don't need you to burn up time trying to draw nice, pretty pictures of what I've already drawn for you.
Mhm.
No, you do not need to do that. But remember that when you're solving your problems, if there's the type of problem where you ought to be drawing some free body diagrams or some illustrations, you know, to kind of support what you're doing, I would recommend doing that. But there's no reason to completely redraw the whole problem statement. You're burning 5 or 10 minutes on a problem just doing that. So no.
Okay, sounds good. Thanks.
Okay. Alrighty. Oh, back to this. See this fellow here? That was Saint Venant. Okay. Do we have any French students? Because I am going to butcher this. Adhemar Jean-Claude Bar de Saint Venant. That's the fellow's name, believe it or not. I can't believe he'd had that on his social security card or his driver's license. But then I guess from 1797 to 1886, he wouldn't have had either. He was a French mathematician known for shallow water equations, of all things. So that he was looking at disturbances and flow of water, you know, like through a shallow channel where you put disturbance like a rock or an island or something, and how the water would flow around that. And somehow all of that brilliance got into this stress flow in materials. That's who he was. The other thing that I did not actually put into the presentation, but the other point about the St. Venant's principle is that if I had one point load, and let's just say this is 100 kips in one point load. Well, directly under that point load, you have some very high stress fields due to a very large load being applied over a small area. But down here at L from the bottom, it would average out to P over A. Now, if you were to replace this load with something that is equivalent, so say instead of one big 100 kip load, you apply two symmetric 50 kip loads. The principle also says that at L distance away from the application of the load, there would be no discernible difference between one big load that equals 100 kips or two symmetrically placed 50 kip loads or 4 25 kip loads. It doesn't matter. As long as the loads are equivalent, which is the total magnitude and the total point of application are equivalent, then at some distance away, the material could not tell the difference. It's still just going to be P over A. That was another point to St. Venant's principles. Okay, any questions on Mr. St. Venant?
Professor, I have a question.
Yes.
Would there not be any disturbance if there was a distributed load?
I believe that is correct.
Okay, just making sure.
Yeah. So if you had a distributed load over instead of a point load, there would be, it's just kind of weird to look at, but if you had this as a line going right down the middle of this and the total magnitude of that line was the same as the point load, then you would still have a little bit of a disturbance across the grain, so to speak. The stress would be non-uniform across the grain, but in this direction, it would be uniform. The only way to apply the load so that like instantly it's totally P over A uniform is if the load itself was a uniform load. So like the load itself was spread evenly in all directions and the load was so many pounds per square inch or so, then it would be equivalent. Any other? Yes, of course. Any other questions on Mr. St. Venant? He didn't look very happy, did he? I mean, not as happy as the other guy. Okay, moving on. Let's talk about the elastic deformation of an axially loaded member. We start with a non-uniform axially loaded member of length L. Okay, so we're going to start in the most general sense. Okay, and we're going to go through, and I'm going to warn you up front, there's going to be some calculus in here. I tried not to, but there is going to be some calculus, but there's going to be a simplified version of it that you will use for most of your work. Not all of it, but most of it. But we're going to start in the most general sense, and for the most general sense, we need calculus to solve it. So here's our general sense. This is a non-prismatic section. It changes as you go down the length. And we can apply a load to this. And N sub X just refers to that N is a normal force and a normal force. But the sub X means that this normal force may or may not be constant down the whole length of the section. It may be dependent upon some distance X from the end of the member. Okay, so if we apply a load, N sub X, where N sub X is a normal force that may vary with distance X from the reference point as shown. So we're going to define, and it's arbitrary, but we're going to define from the left-hand side a distance X, and then we're going to slice this up into little dx's to solve this thing. So N sub X just means that it might be a varying force dependent upon distance X. So far, so good? Okay. Then we might expect a deformation, a stretching of delta if we apply the loads as shown. So we would expect that this material might stretch out a little bit because we are pulling on it, and that deformation is labeled as delta. If we define the following, if A sub x is the cross-sectional area at x, E sub x is Young's modulus of elasticity at x, and usually this is constant, but it could be varying. Not quite sure how you get it to vary, but it could be a variable depending upon x. Then we can say that the stress at any point of x, so say like the stress right here at x, is equal to the normal force at that point divided by the area at that point. Okay, does that make sense to everybody? If the area varies and the force varies, then we can only find the stress at any given point by knowing where x is and knowing what the force is at x and what the area is at x. Is that making sense? Somebody?
Yeah.
Yes.
Okay, thank you. So the strain at any point at x, the strain is going to be equal to a little differential of the total deformation. Okay, so this is the deformation over the whole length L. Over this distance dx, you're going to have a little differential delta, which is here. So the strain is going to be that little differential delta over dx, as noted here. So d delta over dx is inch per inch, the average strain over this little interval. So I have my stress defined, I have my strain defined. Now, since Hooke's law is defined as delta is equal to Young's modulus, actually that's not Hooke's law, that's the definition of strain. Sorry, definition of strain is that the deformation is equal to Young's modulus times the strain. Wait a minute. I think I biffed. Oh, I did. That was the wrong symbol. Sorry, everybody. This is Hooke's law. This is the wrong symbol. Slide 52. All right. Sorry, everybody. This is sigma. So when I go here, that's going to be the right symbol. Hooke's law. Sigma is equal to Young's modulus times epsilon, the strain. There, I can substitute. This is my stress, and my strain was d delta dx. So I just substituted for the stress, I substituted for the strain, and I get this equation here. Now what I can do is isolate d delta by moving everything over to the other side. So d delta is normal force over area over Young's modulus times dx. And then I can integrate both sides, and I get delta is equal to the integral from 0 to L n sub x, a sub x, e sub x, dx. This is the most general form of the equation. This is the general expression. If any of the three variables are constant, which in many cases, all three of the variables, n, a, and e, are constant. If they are constant, then they can come out of the integrand, and you only have to integrate those particular ones that are a function of x dx. Okay, example? Anybody want an example?
Yes, please.
Yes, please.
Yeah.
Now I got some enthusiasm. Okay. Here is what we're given. We are given this steel plate of this shape. It's 24 inches wide at the top. It's 12 inches wide at the bottom. It's 36 inches long. And I am suspending from this little plate of steel 600,000 pounds. The modulus elasticity of steel is 29,000 KSI. The thickness of this steel plate, I just randomly picked a 1-inch plate. So this is actually very reminiscent of a gusset plate in a braced frame. So this is not totally unheard of. And 600 kips is a lot, but you know, some of these braced frames do carry a lot of load. So this is not unheard of. If I measure X from the support up here, like so, then the width of the plate W is a function of X, like so. So now the problem is going to be solve this problem and tell me exactly how much does this end of the plate deform down under 600 kips. What's the deformation at the bottom of the plate? There's none at the top, it's fixed. What is the deformation at the bottom of the plate when you apply 600 kips? Okay, so find the deformation delta of the plate. Solution. Okay, well, if X is measured from the support, like so, then the width of the plate is a function of X. So let me stop here for a moment. Of those three variables that I mentioned, the normal force, the area, and Young's modulus, which ones are a function of X and which ones are fixed or constant?
The width is the only one that's a function.
Okay, so the width is half of the area. Remember the three functions were area, Young's modulus, and the normal force. So yes, what you just said is absolutely right. The area is a function of the width, and the width is a function of X. So A is a variable, N and E are constant. Okay. So the reduction in plate width is linear, so we're going to use an equation for a line. As you can see, these are straight lines. So that means that the plate is reducing in width in a linear fashion from 24 to 12. If this was curvy, you know, then it'd be a more interesting problem. So the equation for a line, W equals, or width equals M times X plus B, you know, linear equation. With X equal to 0, then, and I know everybody knows how to solve a linear equation. I know that was probably many years ago, but sometimes when I do problems like this, I scratch my head for a few minutes until I remember how to do this. So I figure I just throw it in there as part of the problem. So to solve this linear equation, what I like to do is I say when X is equal to 0, so you're up here, then the width is equal to 24. So if I go 24 equals M times 0 plus B, then I know B is 24 inches. And when X equals 36 down here, so W equals 12, when X equals 36, B is known to be 24, I can solve for M. M is equal to minus 12 over 36, just solving this, which is minus 1/3. And so W as a function of X is minus 1/3 X plus 24. So then my area as a function of X is the thickness of 1 inch times the width of minus 1/3 X plus 24, all in inches. And so I get 24 minus X over 3 inches squared is my function for the area as a function of X. Okay, so now I can go to my expression and I can fill in. My normal force is 600, that's constant. My E is 29,000, that's constant. My A is this whole function here. We're integrating from 0 to 36, and we use the dx here. Okay, so I just repeated it up here at the top. So I'm going to pull my constants out front. So this is out front. This is 600 divided by 29,000 times 3. I multiply times 3 to get the fraction out of here. So that all comes out in front, and I need to integrate this from 0 to 36. Notice that all the units have canceled out because I had kip over inch squared times KSI. These all cancel each other out. Using the calculus expression, and by the way, there's many different ways to solve this. If you get to this point here, and how do I solve this? I'm old school. I'm not this old school, but I'm old school in that I would plug this into software like MathCAD or MATLAB or any of those types of problems that will solve something like this. And for me, that's the quickest way to solve it because you can actually type it in and it looks like the equation and it will solve it from 0 to 36 and give you a scalar number. It'll give you the number you're looking for. I believe, although I probably in my lifetime will never have enough time to figure this out, but I believe our TI calculators will solve this now. Something like this you can plug into the TI calculator, but don't quote me on that because I haven't figured out how to do that yet. The really old school way of solving this is to recognize the form of this integrand matches this of a calculus expression. So 1 over ax plus b, 1 over minus x plus 72, this matches this form. So the solution is going to be in the form of 1 over a natural log ax plus b plus c. That's the form it's going to take. And c is your constant of integration. So solving it in this way, I have this whole piece at 0, and I have this whole piece again at 36. So I plug those all into here. This was out in front, and I solve for the natural log of this number and the natural log of this number. And all that is to say, I get 0.04302 inches. That is my total deformation. If this was on a test, could we just use the calculator to solve, or would we need the work? This will not be on a test, is the simple answer. The tests are there to, the tests are there to see that you are understanding and comprehending the material and digesting this and basically getting the principles. This is not going to be a calculus test. There will not be calculus on the tests. I just don't want you to burn up all your time trying to solve something from another class. I'd rather you burn up all your time and cuss at me trying to solve from this class. Okay. All right, so now here's the interesting part about this problem. This is the answer, 0.04302 inches. But here's the interesting part, is that this shape, this oddball shape, with a material with a 29,000 KSI modulus elasticity and 1-inch thickness, I can use some software that I have on my system here to solve this directly without using integrals, without using mechanics of materials principles. I can just plug this in, basically draw this in, and put 600 kips on it and have it solved. The software that I used, I can use eTabs is one. SAP 2000 is another software program. Anything that will do a finite element, visual analysis or RAM or RISA, there's any number of software packages out there that will do it. But here's the interesting part. If I use 3 elements, so in other words, I simulate this with 1, 2, 3 elements, and I let the software solve it, I get a total deflection of 0.637. That's off by like 150%. If I go to 12 elements, like so, I get 0.453, which is getting, now you're in the ballpark. If I use 48 pieces, which looks like so, then I'm at 0.450 inches. And I got tired of drawing this, so I'm not going to draw 192 for you, but you get the idea. Each one of these steps, you take each one of these elements and you cut it into 4 pieces. So each one of these now is going to be quadruple what it was before. And I get 0.444. At 768, I got 0.441. And that's as far as I took it. But you can see how this is converging on the theoretical answer, like so. Okay, any questions on this portion? Okay. Now, what if the normal force equals P as a constant and A and E are also constant? Then what? What happens? Well, then the integral is solved with delta equals PL over AE. Like I said, it's going to greatly simplify if all of these are constants. Okay, so that's it. That's the answer to if all 3 of these variables are constant, that's your answer. That reduces to a very simple equation. If your actually loaded member is actually composed of different segments, where P, A, and E may be constant for each segment, but they may be different from segment to segment, then what do? Well, then you can use this. The deformation would then be equal to the sum of PL over AE of each individual segment. And so that's why this is I equals 1 to n. So if you have n number of segments, then you'll have n number of additions for each individual segment. Okay, sign convention, consistent with previous lectures. P is positive if the load is in tension and negative if the load is compressive. Therefore, delta is positive if the load is in tension and stretches the member longer. Delta would be negative if the load is compressive and tends to shorten that member. Superposition. We have to hit this real quick before we go into the meat of tonight's lecture. Superposition is if a member is in the elastic range. This is the key. It has to be in the elastic range. Then the total load effect or deformation caused by multiple effects is equivalent to the sum of the load effects or deformations evaluated for each effect individually. Here's the illustration. Here I have a beam and it has 2 loads on it. That beam is going to bend over for a total deformation due to these 2 loads. But it may be expedient for us to solve this for 1 load and find the deformation due to that load and solve for this load and the deformation due to this load. The total deformation, delta, is going to be the sum of deflection 1 plus deflection 2. That is superposition. Why does this matter? Why do we care? Well, you'll see how it plays into what we're going to do next, but just in the most simplistic way, perhaps you have a table that tells you what the deflection is on a cantilever due to a point load. but you don't have a table that has due to 2-point loads. So you look it up due to 1-point load, you look it up again due to the other point load, and because of superposition, you can add the two results together for the total result. So that would be an immediate application of superposition. Again, this only applies in the elastic range. Any questions on that?
Oh, thank you.
Okay. All right, so let's do an unrestrained axially loaded deformation problem. Given I have this rod that is made of 2 segments. One segment is 24 inches long, the other segment is 18 inches long, and I have loading as shown. For member AB, the cross-sectional area is 3 inches squared. It is made out of magnesium, AM 1004 T61, that has, from the book's back cover, the Young's modulus elasticity is 6,480 KSI. So A to B is that material. For member BC, the area is now only 1 inch squared. This portion is made out of titanium. Don't worry too much how I connected titanium and magnesium. I used Gorilla Glue, so that's not a problem there. The designation on the back cover of the book is TI-6AL-4V, and Young's modulus is 17,400 KSI for this material. Okay, so what is required is find the total deformation at C due to the loading as shown. Solution. So I'm going to find the reactions by drawing a free body diagram and summing my forces. Generally, a free body diagram and find all your reactions is the first step to any problem. So here is my free body diagram. Here's my known loading. And here is my unknown reactions, because this is fixed at A. Now, I do recognize that it's obvious that the resisting moment is going to be 0. The resisting A sub y is going to be 0 because there's no twisting moment and there's no vertical loads on this thing. So I understand that reaction at A in the x direction is the only non-trivial answer. But for completeness, it is fixed, so you could have 3 unknowns. I'm going to sum my moments about A, and I have 20 kip through 0 eccentricity, plus 10 kips, again through a 0 eccentricity, minus my reaction in the moment. And so R sub AM is equal to 0, as you could just tell by observation. Sum the forces in the x direction. This one is not trivial. I have drawn RAX in the right-hand direction, so I got that positive, minus 20 plus 10 equals 0. So RAX equals 10 kips to the right. Remember, reactions are always designated by arrows. Internal loading or internal forces are designated by positive or negative, not by arrows. Sum the forces in the y, that's trivial. There are none. RAY is equal to 0. Now that our reactions are found, we're going to use cuts to find internal forces. I have 2 regions, I have 2 segments, and so I need to find what the internal force is somewhere along AB and the internal force somewhere between B and C. So we draw a free body diagram for cut number 1, and I have my 10 kip reaction, and I have an unknown FAB in member A to B. So I sum my forces. Oh, before I sum my forces, I tend to draw my unknown forces in tension. It tends to work out better when you draw them in tension. Even if it's obvious that it's getting compression, go ahead and draw it in tension anyway. That way you keep your signs in the right direction. Sum your forces in the x direction. I have 10 kips plus FAB equals 0. FAB is minus 10. And there's what I'm trying to say. Mathematically, it is minus 10. So therefore, I know it's in compression. Draw a free body diagram for cut number 2. Here we are. Here's my 10 kips. Here's my minus 20 kips. Here's my unknown FBC drawn in tension. And I sum the forces in the x direction. I have 10 kips minus 20 kips plus FBC equals 0. FBC equals 10 kips tension. Okay, so now I know the normal force in or P in A to B and from B to C. A to B is minus 10, B to C is positive 10. Any questions on what I've done? Okay. Now with the internal loading solved, draw an axial load diagram. Okay, from A to B, it's minus 10. From B to C, it's positive 10. What do you notice about the axial load diagram? The loading is constant.
Oh, I was gonna say it equals 0.
Only equals 0 at the very ends, really. But the important part of the axial load diagram is now when you do the cuts and you solve the cuts, you're kind of just getting a snapshot at one point. But when you draw the whole diagram, you see what is happening inside of it over the whole length from A to C. And now you can see over this whole diagram that from A to B, the load is constant. And from B to C, the load is constant. So what does that mean? That means you don't have to solve an integral. That's what it means. It means you can use the equations without solving integrals. The integrals are only needed if these were not constant. If these varied in some way, a linear or a parabolic, if this was not a flat line, then you'd have to use an integral to solve this. They are constant. So with the axial load diagram, you can now see that for segment AB, the load is a consistent, even though I can't spell, minus 10 kips. And for segment BC, the load is consistently positive 10 kips. Because each segment, N sub x, E sub x, and A sub x are constant. They're not constant through the whole length, but they are constant for each segment, A to B, B to C. We can use the summation equation. Summation equation, as I presented. So N is equal to 2. I have 2 segments. So we're going to do PL over AE for A to B, PL over AE for B to C. P is minus 10 on A to B, and P is positive 10 from B to C. Please don't get hung up on P or N. Doesn't really, they're kind of interchangeable. N just refers to a normal force, and P is kind of referring to a force, just a generic force. And I used FAB and FBC to describe the forces as internal forces. These are all interchangeable. The key is that you recognize that internally, the segment A to B is resisting minus 10 kips, and B to C is resisting a positive 10 kips consistently. Okay, is everybody all right with that?
Yeah.
Okay, I got one yeah. Do I have any no's? Anybody not okay with that? again, I don't have the privilege of looking out and seeing all of you at the same time, so I have no idea if all 29 of you are going, yeah, this is easy, keep moving. Or if half of you are eyes glazed over and drooling. I have no idea. So, okay, I got a processing. That's
I
good.
have a question.
Sure.
Let's say the 10 kips is not constant.
Okay.
So you're gonna need to integrate from A to B and then add the integration from B to C as well.
Okay, so you're saying instead of being constant, what if the load looked like this?
Yeah, or a curve.
Okay, well, yeah, you got to integrate this. So another way to say integration is the summation. So you could actually just get the area here without actually using an integral symbol. You could get the area of this because minus 10 times 24 is actually minus 10 times 24. That's this area. That's why I want you to draw the axial load diagram. It is so instructive to draw the diagram. This minus 10 times 24 is the area from A to B. So you don't necessarily have to use an integral like I did on that last example. You could, see if I can grab, no, I can't. Ah, there it is. Maybe, there we go. Okay, so you can even have something that looks like this, and you have to have the area and the area. So when I say the integral, you're actually adding up the area. But from segment A to B is this term. And if segment B to C was constant like it is, this term would still look just like it does. Does that help?
Yeah, thank you.
Okay. All right, now, E was given. Yeah, Mustafa, go back to the beginning of example 2. And I said that this is magnesium and this is titanium. By identifying the materials as magnesium and titanium, then E, this E, and this E came from the back of the book cover. Okay? Okay, so now solving this, what I get is a net compression of 0.002 inches. And how do I know it's a compression? Because it's negative. So what was really happening was segment A to B is shortening. Segment B to C is elongating because this is in tension, this is in compression. But look what happened. A to B is a longer segment and it's a much softer material. This material has the stiffness of roughly a third of this material. So under the same load, this one's compression, this one's tension, this shortened a lot more than this one elongated. So you have a net shortening from A to C. So this point out here at C actually moves to the left by 0.02 of an inch. Yes, Dima and Adriel, yes. Remember, calculus is just finding the area under a curve anyway, right? That's the whole point of calculus. We took 3 semesters of calculus to figure out how to find the area under a curve. If you remember, or if I remember right, that was a long time ago. But so if you can get the area under a curve by observation, then you don't need calculus to find that area. But if it's a parabolic or some higher order equation that you cannot eyeball the area of, then you have to use calculus to evaluate it. Does that make sense? Okay. All right, now we're going to move to a new topic. The last one that we just did, let me flip back here real quick. Okay, the last one we just did was a unrestrained axial deformation problem. Unrestrained means that it's fixed on one end, but it was completely free to move at the other end. So guess where we're going next? Statically indeterminate axially loaded members. Oh boy, now what have we done? Now it's fixed at A and it's fixed at B. We have two unknowns, don't we? We have an unknown reaction, horizontal reaction at A, and we have a horizontal unknown reaction at C. Disregarding the trivial solution of the vertical at A and the vertical at C are equal to 0, the rotational restraint at A and C are both equal to 0. So we're throwing away those 4 trivial equal to 0 solutions. That's why this is known as an axially loaded problem. So I'm only looking at forces in the x direction, but even in just the x direction, I have 2 unknowns, and I only have 1 equation to sum forces. So I got a problem, don't I? This is 1 degree indeterminate. Summing the moments and summing the forces in the y are trivial and yield only 0 force, so those don't help me. We will derive a second equation by comparing the relative rigidities of the 2 segments, A to B and B to C. Here, we're going to present 2 methods to find unknown reactions, namely a compatibility method and a flexibility method. I do have one eye on the clock, so I'm thinking we're going to do, hopefully we'll get through 1 method tonight, and we will pick up the flexibility method at the beginning of next Tuesday. So the compatibility method, we will start by exploring an example as shown. Here's our example problem. I have a rod of A to B to C. The total rod is 5 feet long, and I have this load applied somewhere in the middle of the rod. So the area of A to B is equal to the area of B to C. So it's a consistent rod all the way through, and the area is 2 inches squared. This is going to be a steel rod, so the modulus is 29,000 KSI. The goal then is to find horizontal reactions at A and C and to find the force in each segment. What is the force from A to B? What is the force from B to C? We will start by cutting a free body diagram of segment A to B. So this is what it looks like. So I have my end here. I still don't know anything about it. And I have an unknown force A to B. Somewhere in here, force A to B. Due to this force A to B, I see that when I'm isolating, we see there's an unknown force assumed in tension, FAB, acting over the entire length of A to B. If AB were an isolated member, if it were, then that force AB would cause a deformation, delta AB, as shown. Okay, so if this were the whole problem, then this force would cause this deflection. I know it's not, but that's the compatibility method, is breaking up a complex problem into bite-sized pieces and solving them 1 piece at a time. So that's how it works. I am going to virtually imagine that A to B is just an independent rod that is unrestrained. I have this unknown force that causes this unknown deformation as shown. Because the force FAB is constant over the length of AB, we can use the deformation equation. And how do I know that FAB is constant over this length? I know it's constant over this length because my load is applied here, and my only other effect on this is my reaction at A. There's nothing else in between. So there's nothing else between A and B that would change the force So the force has to be constant between A and B. So because the force is constant between A and B, we can use the deformation equation. Delta is equal to FAB L over AE. So the only unknown in this is FAB. The length is 36. The area is 2. E is 29,000. And so I can write this in terms of FAB, that delta AB is FAB over 1611.1 kips. So far, so good, everybody? Anybody? I got a yay.
So far,
Okay.
so good.
So far, so good. Thank you. Make sure you're still awake. Now we will look at the free body diagram as segment BC. Okay, so here's the other half of it. And again, I have some unknown force BC that is acting over the length of BC. And that force is going to cause a deformation as shown. So this force is compressive because it is the opposite of the other force, which was tensile. So if FAB tends to drag B over to the right, then FBC would tend to drag it to the right as well.
Would
Yes.
that all be like perspective? Because if we were to say that FAB would be dragging it to the left, then would it be like the opposite? What would change?
Absolutely nothing. The point is you have to be consistent. That's all. But that's a great
Okay.
question. But this is all virtual anyway. This is all an idea in our head, is an imaginary idea. It doesn't really separate like this. So you'll see how it comes together at the end. But if you assumed to the left at the beginning, you'll get exactly the same answer as assuming to the right at the very beginning. Okay, but imaginary, we have this force, we have this deformation. So the deflection at BC is this unknown force BC, L over AE. And now we plug in this L is 24 inches, and the material is still 2 inches and 29,000. So I get FBC over 2416.7 kips. Now for the compatibility part. The two segments are attached at B. They cannot deform relative one to the other. So that forces that the deflection at AB plus the deflection at BC has to equal 0. They can't differ one from the other. So they have to equate to 0. That doesn't mean, well, let me just leave it at that. That these two deformations have to equal 0. So back to the question a moment ago, if this one was negative, then this one would be positive. But if I assume that this one is positive, then this one would be negative. And so it does wash out in the end, whatever your initial assumption might be. Okay, I know we're getting whistle bit here, only got a couple minutes. This is not to say that node B doesn't move. It does. This is just to say that by however much segment AB grows, consequentially segment BC must shorten by the same amount. Or the opposite, however much segment AB will shrink means segment BC will elongate by the same amount. Because overall, the whole thing still is 5 feet long. It's forced between two hard points. It can't be anything other than 5 feet long. Okay, so that does mean that delta AB is equal to the negative of delta BC. So I substitute my equations for what I know about delta AB to delta BC. And I have this now relationship between FAB and FBC, where FAB is equal to this proportion of BC. Now that we have an expression that relates to two internal forces by rigidity, we now have two equations for two unknowns, and we can solve for our reactions, which we will do next time. We have a matter of seconds. Who has a question they'd like to ask in the last 30 seconds? Okay. Very good. I have written this syllabus, this course, to have a little bit of fluff in it from now and again. Oh, good question. Mustafa, very good question. We are now in chapter 4. And St. Venant's principle was 4.1. The integral calculus stuff was 4.2. And we are now plowing forward into, bear with me, we'll get there a second. 4.3 was superposition, and we are now in 4.4. And we will pick up on 4.4 and continue on next Tuesday. Any last minute questions for me over the weekend?
Yeah, Professor, one quick question for the midterm.
Yes.
Is it all gonna be calculation questions, or are you gonna ask also about like theory?
They are mostly going to be problem questions. So for the most part, they will look like a homework problem, but they will be written in such a way that you can spend roughly 20 minutes on each one of them to solve them. So it's not going to be as involved or as many steps as some of the homework problems had, but it will be testing the same principles and same ideas as the homework problems have. But they will be problems. So you'll be given a diagram of a rod or a beam and a cable and some loads or whatnot, and you'll be asked to solve the problem.
All right, thank you.
Okay, and we'll talk more about that as we get closer. Again, today was just to wake everybody up to say, oh, we got 2 weeks. We got a test coming up in 2 weeks, but we'll talk more about that. Okay, so I'm gonna end the session. Everybody have a good evening and a good weekend. And I will be back on Tuesday. Thank you.
Well, thank you.